up of HICO data to the entire community. Next, we're going to really transition to a very different discipline, and this is a discipline focused on microgravity. And so just to remind those of you who've been with us for a few years, this chart was presented by Peter Voorhees, or this image, to remind us how powerful it is when you go into microgravity and you don't have buoyancy-driven or thermally driven convection. And that allows you to study a number of different processes in material solidification, in smart materials, and as our next presenter has done on the ISS for a number of years, in magnetorheological fluids. And these are all materials that have such important applications around the world. So I'm very pleased to introduce Dr. Eric Furst to talk to us about his work on the International Space Station.
Thanks, Julie. Let me just log in here. It's a pleasure to be here and to have the opportunity to present some of our work that's been conducted on the space station. This has to do with building things from tiny particles, basically. And before I get started, let me just acknowledge that this is very collaborative work. I'm merely here to present in front of you some of the outcomes that we've had. I really want to highlight the opportunities that people have had in the development of their professional careers, including James Swan and Paula Vasquez. These are two postdocs that have worked with me over the period of our in-space experiments, our ISS research experiments. You can see that Jim's now joining the faculty of MIT, and Paula Vasquez took a position in applied math at the University of South Carolina. I also want to acknowledge our collaborators, Alice Gast, Jan Vermont, Eric Dufresne, Patrick Hopkins, and Anne Grier, who have been working with us on nanostructured materials. This long title here, Overcoming Kinetic Barriers to Self-Assembly, Field-Directed Colloidal Phase Transitions, this has to do with how we build things from tiny particles. So you could really think of this as making nanostructured materials from tiny building blocks, or how ISS research has helped us learn how to create nanostructures from very tiny particles. And I think you'll see, I hope I can convey in this talk, that this is a pretty exciting point in the development of nanomaterials, that if we think about using small building blocks like nanoparticles and colloids as means to create new nanostructured materials, we'll create a lot of new technologies for both Earth and space applications. Part of that comes from the fact that nanostructures give us unique function. The reason that we want to pattern or create structures on the nanometer scale, and I should just take a second to think, we were just speaking about things on kilometer scales, and now we're 9 to 12 orders of magnitude smaller in scale in this talk. But the reason that you want to template or structure matter on these length scales is because those length scales then interact with energy. They interact with chemical species. They interact with how light and charge move around in materials in unique ways. One example shown here. This is the i7, the Intel i7 microprocessor. This is one form of a nanostructured material, or a nanostructured device. Transistors today now are on the order of tens of nanometers in dimension, and we could all agree that the idea of that making these small devices, right, enables new performance and new power that we didn't realize, we couldn't possibly realize even 10, 20 years ago. That all has to do with how charge is manipulated and moves around in that microprocessor. It allows us to do calculations and computations. Now, the materials I want to talk about aren't this sophisticated as our microprocessors, but they still convey, or they should have new and unique performance that we can make use of. So let me think about a few ways that we can use nanostructure and create new types of functionality. One example shown here, this is a homojunction photovoltaic. This is a typical sort of PN junction that you're going to see in a photovoltaic application. Light is absorbed by this PN junction, and excitons created. That's the tightly bound positive and negative charge. That's going to diffuse around, and it has to make it to the interface of that PN junction in order to separate and create that current that you want out of that photovoltaic material. If you think about it, there's a way of structuring that matter that makes use of two important transport length scales, two important length scales in this material. That is, you want to have a large length scale to absorb light over, right? I want to have enough material I can collect a lot of light. But if I make that material really thick, I can create excitons which are very far from that interface. So it's not going to help me with generating current. But if I can somehow get every interface just nanometers away from that exciton, where those excitons are generated, I can create a material that's going to be more efficient. And that's the basis of a heterojunction photovoltaic. So by merely patterning the matter in a different way, making cylinders instead of just that planar interface, you can think about taking advantage of how light is absorbed, how charge is transported, and creating a new material that allows you to more efficiently absorb and convert light into current. That's one example, one idea of how or why we want to make nanostructured materials. And in fact, these devices have been built using exactly the same fabrication methods that microprocessor was built with. It's by using silicon fabrication technologies that have enabled us to make and have been developed over the years to make microprocessors. We think of that as a top-down manufacturing process, one in which we deposit and remove layers of material in a number of steps. And those use costly fabrication methods and costly fabrication factories. Fabs right now are on the order of about $5 to $10 billion if you're going to make the investment to build a new one. We can also think of other ways that we can structure materials. We can create a thermal barrier material, ultra-low thermal conductivity material, using the same fabrication methods by drilling tiny holes, essentially, in a silicon substrate. And the way heat is transported through phonons, that is the vibrational modes of those atoms, and how those phonons scatter off of those holes, creates this ultra-low thermal conductivity material. So that's why we want to create nanostructured materials and what we can gain out of that. The question that we pose and that we're excited about is the idea that, well, what if I could take a mu of a material, just some random material, right, that can be cast or printed or coated onto a substrate, and what if that material could self-organize into those unique nanostructures or microstructures? Well, that's what we're interested in. That's where the self-assembly of nanoparticles comes from. And I hope to tell you a little bit about, you know, how we're doing that and how the ISS research program has helped us move along in this. So that ultra-low thermal conductivity material, we can generate the same sort of properties by taking nanoparticles and organizing those nanoparticles, or really have them self-organize as we deposit them as thin layers to create new thermal barrier materials. And this is just one example. This is a unique length scale of matter to manipulate, and I think you'll see some of the challenges of this as I go on today. So, but what it will enable, I think, for us in space and on Earth are really what we're looking for: new nanomanufacturing processes, ones that are highly scalable. And we refer to these as bottom-up assembly processes. That is, that the structure of the material self-organizes, and so that you can really start with one of these casting or printing methods over large scales very inexpensively and still create, you know, fantastic functional nanostructured materials with new properties more efficient properties or something like that. So the applications are in any way that nanostructured materials can manipulate light or charge or heat or other forms of energy and mass. And they include applications in energy, advanced coatings, and photonics, and new materials that we're just dreaming up right now called phosonics that allow you to manipulate both sound and light simultaneously. This is all made possible because nanoparticles are really a form of colloids. And colloid is a term that refers to a unique length scale of matter. You saw how that length scale impacts functionality, right, in terms of transport of charge and energy, et cetera. But how that length scale impacts us in forming nanostructured materials is the fact that they exhibit this wonderful phenomena of Brownian motion. You can see that in this video here. These are colloidal particles. These are micron in dimension. To give you a little bit of a length scale, off to your right, you can see there's a microscope image of a hair. A human hair on the average is about 100 micrometers in diameter. So there's an image of that UD symbol with those colloidal particles about to the scale of the human hair. higher. Now we're holding those particles with what are known as optical tweezers, with light. They're small enough we can actually manipulate them with light. And you'll see that when we turn those tweezers off, the particles start to diffuse around. They exhibit this Brownian motion. That's the inherent nature of the colloidal length scale. It's matter that we can think of as macroscopic in many of its properties, yes, yet it's tiny enough, it's small enough that it can feel the forces of random molecular collisions around it so that they agitate and they move around. Okay? Now, what that allows us to do, or what that enables in a colloidal suspension, is the fact that those particles, because they can move around, they can reconfigure themselves, essentially. And that's the basis of how they can then self-assemble. By changing their interactions, by changing their shape, we can use thermodynamics to predict the structures that these suspensions are going to form. And that's really the basis of that self-assembly or self-organization. And that's been done over the years. These are some examples of just very simple spheres, particles that exhibit what we call hard sphere interactions. So they're like billiard balls, but they're microns in dimension. If you concentrate these particles up sufficiently, they go through a thermodynamic phase transition from a fluid-like state. You can see that on the images to your left, where you just see a blue or a green color of the suspension, to that image in the center and maybe off to the right, where you start to see Bragg diffraction off of little colloidal crystals. That's showing you that you've created a length scale of matter now that's interacting with light. It's diffracting the light in ways that then change its transport. And that's just a very simple self-organization principle, but it's thermodynamically driven. In fact, gem opals are essentially silica particles that are about 300 nanometers in diameter, which are precipitated out and organized on geological timescales to give us that beautiful iridescence. So these are found in nature. Now, why we're really at an exciting point in this form of research is summarized by this slide. The building blocks that we have available to us now have grown just exponentially over the past 10 or 15 years. Synthetic chemists, inorganic chemists, chemical engineers, physicists have grown exceedingly creative in their syntheses of tiny building blocks, uniform building blocks from which we can start to manipulate matter. And so what we can form out of these, how we form those, are the key questions. But we think that these are going to enable our new nanostructure materials and applications. I'll just show one example. This is an example of dumbbell particles. Take those spheres that I showed earlier. These are particles that are now two spheres essentially smashed together. And what you see is a colloidal crystal that we've grown from those dumbbell particles. And the particular crystal form that we can grow, the simple monoclinic structure, is dictated essentially by the shape of that particle and by thermodynamics. That's the equilibrium structure you would expect as I pack particles of that shape up at higher and higher concentrations. So again, thermodynamics gives us a roadmap to predict the types of structures that we're going to form. Changing particle shape, changing particle interactions allows us to create new nanostructures. You can see that on the lower your lower left, there's an image of a little bit larger length scale. Again, beautiful colloidal crystals diffracting light, and those are those dumbbell crystals. And it's hoped that these will create, for instance, new energy-efficient color displays. If you think about your Eink displays in your readers that you have today, those are all basically colloidal suspensions that are manipulated by electric charge. What they lack usually is color. And maybe diffractive elements like this will provide us the reflective color properties that we need in those types of displays. So that's one potential application. The challenge is this. Thermodynamics tells us what we'll get eventually. And I'm showing here in your top right a phase diagram. This basically shows, as a function of concentration on the vertical axis and the aspect ratio of those dumbbell particles on the horizontal axis, if I pick a different point in that, it's going to tell me what the equilibrium phase of that suspension is going to be. It could be an FCC crystal, you see, it could be a disordered fluid. Eventually, at the right aspect ratio and the right concentration, we can form, or we should be able to form, those close-packed crystals that you saw. So by taking the right aspect ratio and concentrating them up, that's how we should be able, based on thermodynamics, to form those nanostructured materials. Here's the challenge. Oftentimes you can't get there. There's a kinetic barrier to getting there. Although thermodynamics tells us what we should be able to get, right? Kinetics tells us whether we'll get there on a time frame that's relevant to us or not. So there's kinetic traps, there's bottlenecks that hinder the formation of these thermodynamically driven phases, those beautiful crystals that we want to create. This is an example of a non-equilibrium glass, essentially. This is a random packing of all those dumbbell particles. And you can think that it's natural to expect this in some ways, right? As I start to concentrate particles up, higher and higher concentration, it becomes less efficient for them to move around and find lattice spaces to form these beautiful crystals on, right? To move, they have to move their neighbors have to move their neighbors, right? It becomes a collective phenomena. And it's exacerbated, there's a slip. It's exacerbated when the particles become anisotropic, or they become patchy, for instance, because not only do they have to translationally move around, but they have to rotate, so their neighbors have to rotate. And then there's nucleation barriers also to form these crystals. So this is an inherent aspect and a major limitation of trying to build nanostructured materials by self-assembly using nanoparticles. So there's this glass that frustrates us. And what we found is that using external fields to just nudge this process along, essentially direct this self-assembly, has become essential to forming these types of crystals. That's essentially, that's how we built the beautiful simple monoclinic crystals out of dumbbells that I showed you earlier. I'm not sure if that video is going to, here we go, it'll play now. So what we typically will use, for instance, with these particles is an electric field. The AC electric field induces interactions both between the particles, but also orients them. And that orientation removes some of the degrees of freedom of those particles and allows us to pack them together then into these equilibrium phases. So we can nudge the process along using directing fields. And it's this process of using directing fields that we studied on the International Space Station. So let me tell you a little bit about the experiments that we did, and then give you some results again that are derived from those studies. So these were experiments that were conducted on, this is in Space 2, was conducted on expeditions 16, 18, 19, and 20. And I want to acknowledge this list of astronauts, including really Peggy Whitson, who produced the majority of our experiments, just countless hours of experiments for us, and just was this amazing, engaging person, as well as the other astronauts as well. But we had a lot of fun working with her, and just that human element of having hands in the experiments, digging around, making observations, sometimes the serendipity that comes along with that really drove the science of this project, and it was really an exciting time for us. There's Peggy doing, there's an image of her in the lower right doing an experiment on in the microgravity sciences glove box where our experiment is. And this work was published just last year in the Proceedings of the National Academy of Sciences. The experiment is this: to study this field-directed nature of self-assembly and to try to overcome these kinetic limitations, we took another model fluid called a magnetorheological fluid that's field responsive. Now, instead of responding to electric fields, these particles, these are colloidal particles, they're about a micrometer in diameter. They respond to magnetic fields. They essentially become little magnets, little dipoles when we place them in a magnetic field. And those dipoles then can interact and line up with one another, much like the particles interacting in the electric fields that I showed earlier. They're dilute suspensions. They're suspended in water, so they're pretty benign. And what we do is essentially in the experiment, we have the sample between two Helmholtz coils. It's going to generate our magnetic field. And we can, with the apparatus on board the MSG, we can look at the structure of the suspension and take video microscopy data, basically. And what we're looking for is whether that we can start from a non-equilibrium jammed state and somehow get that suspension to form an equilibrium state, somehow direct the phase separation with that field. So how we're going to do that is we're going to toggle the field on and off with certain frequencies, and we'll use different amplitudes of the field strength. Most of the images that I'm going to show you were taken perpendicular to the field direction. So in that lower sequence of images, you can see the structure of our suspension changing with time. It starts off black because the particles are basically throughout our entire volume. So no light's making it through our samples. But as the suspension coarsens, you can see light starting to make it through. The black regions are the condensed structures of the colloids, and that's where we think that we're forming our equilibrium phases. Now, here's an experiment on ground just to show you what happens when we just place these particles in a magnetic field and the structures that they form. It's this web of arrested, this percolated network of particles. All right, this is about 1 millimeter across, so these particles are much smaller than you can see, but you can see this sort of web structure. Right, that's not the equilibrium phase. That's another arrested phase, and it's related to gels essentially. In fact, actually, the ground-based applications of these materials rely on this type of structure. That's where magnetorheology comes from. You can imagine that when I form that structure, it behaves almost like a solid. And so this yield stress behavior allows me to make a transition from a liquid to a solid very, very easily. And these materials are used in clutches and different types of dampers in some of their applications. Here's what the structure looked like in the in-space experiments. Now, for those people that watch the KU band routinely, I was told that this is known as the green blob experiment. But in fact, some of them may be in the room. In fact, actually, we get a lot of very useful data out of this. We're looking at the suspension structure with time. You're going to see an accelerated video, essentially, of that structure changing. And these are under conditions in which we see this phase separation. So we've picked a toggle frequency and a toggle field strength of our magnetic field that drives it to a new equilibrium structure. So you can see the structure coarsening. You'll see in this case, this experiment was done by Peggy. You'll see her refocusing and moving around, looking at the sample. And you can see slowly the structure coarsening with time. And then eventually, we're going to speed this up. You'll see the structure really kind of take off in terms of the coarsening kinetics. It's really going to start to phase separate, much like really oil and water would phase separate. So there we're refocusing around before we went into the accelerated imaging, and there you go. You really see just those structures just condense or collapse right out of solution. So that's the phase separation that we're looking for. And then when we turn the field off, those particles just diffuse away back into the liquid state. So what we did was we characterized essentially the length scales of that. We measured the width of those aggregates that you saw in that video and plotted those versus time. And I promise this is really the only massive data set that I'll show. But that width versus time is shown here for 33 experiments. So these experiments take 1 hour to 2 hours. You can imagine the dedication and the time that the astronauts provided for us. But the data set was extremely rich. What you see is that they all have this sort of hockey stick shape to them, right? They start off where the width is just changing very, very slowly. This is a logarithmic scale, so it might double in the time of half an hour, just hundreds of microns. And then, in some cases, it really takes off. You see that really collapsing or condensing state. In other cases, it just remains sort of arrested. This gives us the insight then into what conditions it takes to form the equilibrium state when we're nudging it along by these external fields. So for instance, this just shows the 2 different states that we can arrive at the end of our experiments. Ones that haven't coarsened much over time or at all, and ones that have collapsed and consolidated into this, what we think is the equilibrium phase. So what our ISS experiments showed us was the optimum frequencies, basically, to work at when we're using this pulsed field experiment. When we're using pulsed fields to try to self-assemble colloidal or nanoparticle structures. That's summarized in this plot, just showing the distinct line that we found in our experiments between frequencies, pulse frequencies, toggle frequencies of our field, which remain in this arrested non-equilibrium state, and on your left, the frequencies and field strengths that we're able to equilibrate. Okay, so let me just show you what this looks like. We came back and did experiments in the laboratory, ground-based experiments that could validate these results that we got on the International Space Station. And we've had some pretty neat results recently, and I'd like to show those to you. This is this phase separation now done in a ground-based experiment. And you can see, really under the right conditions, this is toggling the field at about 0.66 hertz. That's sort of a magic frequency we found on these ISS experiments. You can see how that suspension structure, instead of arresting, just breaks up into these wonderful droplet-like phases, right? And these are these colloidal particles that are all sort of condensed together now into these highly condensed structures. And playing around a little bit with the toggle frequencies and field strengths, we've been able to actually show that we can create now structured equilibrium phases out of these. Let me just play that again, because this is, I just think, really fun, where you can really see this breakup phenomena. And in fact, actually, you can see this sort of pinching phenomena. It's like a really plateau instability that we're studying right now. Now, this is a little bit different than our ISS experiments, because this is all squashed down on the bottom of a microscope slide. So this is a little bit more of a two-dimensional equivalent. Nonetheless, the physics that we learned in space translate very nicely over to the lab. Okay, well, actually, I'm very close to wrapping up here. So let me just show you the nice thing about our ground-based experiments, and we hope that with new installations coming aboard the ISS, we can do the same on our space station experiments. But we've actually been able to show under the right conditions that those condensed structures that you saw in that last video, actually, if you use a higher magnification and you look at those, you can actually pick up the structure of those phases, and they are indeed crystals that are forming in those condensed phases. In fact, we're very limited in our microscopy because of the opaqueness of these particles, but we can image one or two layers into those structures, and you see that in the red and green image right about at the center of that. Those are actually two stacks of our microstructure. And so each stack is essentially a crystalline structure, and you can see how the particles are stacking on top of one another. Off to the right of that, what we've been able to show is that that is actually the body-centered tetragonal structure that we would expect from the equilibrium phase diagram for these particular particles experiencing essentially a dipolar interaction induced by an external field. So that shows us that we can create equilibrium structures using these directing fields, and I think really gives us this idea that this will help to enable self-assembly of colloids and nanoparticles in this sort of new bottom-up fabrication process that will really, I think, for ground-based and even space-based applications, enable low-cost, large-scale manufacturing of nanostructured materials. And those directing fields are essential. Remember, those are the essential components to avoid the kinetic traps and bottlenecks of self-assembly. As we start to work through this library of nanoparticles that's been created, it's exciting to think about what kind of structures we'll actually be able to build. And in fact, there's a really interesting sort of open challenge for us, which is to say, given a structure that I want to create, that I can predict from understanding how light or charge or chemical species are going to move through a material, right? Similar to how I want to build those pillars of the heterojunction photovoltaic, can I identify the right building blocks and the self-assembly pathway to get there? That's really an open challenge for us for future work. So let me just again acknowledge our collaborators, especially the two postdocs that worked very closely with me and our Glenn research scientists over the years to make this work happen. Jim Swan, who's going to be at MIT, and Paula Vasquez, who's at South Carolina. Also want to acknowledge the previous PI of this project, Alice Gast, who really got this started. The ISS astronauts, again, who made this happen, and our support at Glenn Research Center and Zen Technologies, without whom none of this would have happened. The paper the work that I talked about is online. It's open access at PNAS, so go look it up, and I'd be happy, I think, later to take questions. So thank you for your time.